This call is now being recorded.
Now the question is, which I
Sir,
also asked, that why would we, yeah.
sir,
Yes, go on.
can you please explain this, sir, how we are joining the line from core, interior, rim, this line, sir?
Did I not say yesterday, or who was it?
Yes, sir.
Your
You
question is,
mentioned it,
how
sir. But
do we get the, sorry?
yes, sir. You explained it yesterday, sir, but I couldn't clearly get it, sir.
Okay, so the question is, how did we get these lines?
No, sir. I mean, why are we joining this yellow line from core to interior to rim? How do we know this that we have joined
Why
this
do
line?
our join? Okay, did we get it? Did you get that? Why? How did we get these lines?
Yes, sir. I mean, you are saying about the points, sir. I mean, rim point, interior point, or core point.
Yes, this blue, let's say this blue line out here. Okay. So how did we get this? How did we plot this
Yes,
line?
sir.
I guess you all have understood, because that I explained quite something. Okay. So now what you have understood probably is that the
Yes, sir.
intersection of these blue lines is this blue point. Is that correct?
Yes, sir.
The intersection of these two blue lines, okay, which we have got from the composition of the core. Did Ravi got disconnected? No. The interior of the core, from the composition of the core, we got this temperature sensitive equilibria and the pressure sensitive equilibria from the thermometer and the barometer. And the intersection of these two lines is the pressure temperature condition at which the core formed. Did you understand that concept?
Yes, sir.
Okay. Now the same thing, the red lines is the composition. We have drawn this line using the composition of the interior of the garnet and the interior of the biotite and plagioclase. And the intersection of the two lines gives the pressure and the temperature conditions of the formation of the interior of the garnet. Okay. Similarly, the green lines, the two of the green lines we have got using the rim compositions of garnet, biotite, and plagioclase, and therefore the intersection of the green lines is the pressure and the temperature condition at which the rim of the garnet forms. Now you think of a garnet grain.
Yes, sir.
Okay,
Now I got it, sir. That
how
was
does
my
it
doubt,
grow
sir,
with time?
about.
Okay, how does it grow with time? That is the core. Okay, any grain, any mineral grain starts with a small, it doesn't land up big. Okay, it starts with a small nucleus, right? It starts with a small nucleus and it starts growing.
Yes, sir.
Okay, now we are thinking of a garnet which took a long time to grow, not only the garnet associated biotite and plagioclase, which took a long time to grow from the core towards the rim. So this is the core, this is the rim. Okay. Now, as the compositions are different, okay, the core formed at a pressure temperature condition which is different from that of the rim, because the compositions are different. If would have formed at the
Yes, sir.
same pressure temperature conditions, it would have had the same composition. Now, what we observed is the composition from the core is different from that of the interior and different from that of the rim. So obviously, what formed first? The core.
Yes, sir.
If you look through time, what formed first? The core,
Yes, sir.
followed
Yes, sir.
by the
Core and then
interior,
the
and and
and
then
then
the
the
rim.
rim, sir. Yes, sir.
So we have got three different points, the blue point, red point, and the rim point, which gives the pressure and the temperature condition of the formation of the core, the formation of the interior, and the formation of the rim. Okay, from a single
Yes, sir.
mineral. So we have joined this line now with the yellow, but the question is, which direction
Yes.
is it moving? Okay, the direction it would move in the direction in which the mineral has grown.
Yes, sir.
Right? The core is older. So we will always move in the direction of younging time. So the rim is younger.
Yes, sir.
Okay, so then the path will move from the older towards the younger direction. And that's why we have joined the core, the interior, and the rim. And after joining
Yes, sir.
this becomes a path.
Now I got it, sir.
This becomes a path. Yeah. Okay. And this is a part of the pressure temperature
Yes, sir.
path. This is just an example to show
Yes, sir.
that
There
how
is
we
too
can
much
use.
lag in the sound, sir.
That I do not know because I'm connected on the LAN.
No, sir, that's not the
For
problem, sir.
me,
It's taking too much time from me saying and you replying, sir. There is a lag in that between, sir. Not the internet connection, sir. That is, I think, fine, sir.
Okay. So now, as you have understood, let's move on.
sir, just a little question like here, like sir, you can see like rim's temperature is less than like interior, but we know like in crystal like core temperature is less. As we go from core to rim, the temperature is like increasing. So the rim should like it's just a like theoretical
No,
question
it
like
depends. Obviously, it depends on how when the crystal or the grain is forming. Okay,
okay
when the
sir.
grain is forming. In some situations, we definitely form the grain. See, the temperature remains practically the same, right? It's the pressure what is changing. Okay, so it sometimes with changing pressure and temperature, different minerals, it depends upon the stability fields of those minerals. Okay, it's not a kind of a common thing or a straightforward thing that you always get the core having a particular or the lower or a higher temperature and the rim having the same. Okay, it
Okay,
is somehow you can correlate this in an igneous rock when a certain crystal is crystallizing from the melt, then always that the core will be formed at a higher temperature and the rim will form at a lower temperature because this is crystallizing from a melt in an igneous system. But in a metamorphic system, okay, minerals can grow with increasing temperature and pressure. Minerals can grow with decreasing pressure and temperature as well. And depends on which mineral is growing, depends on the stability field of that particular mineral.
okay
Okay.
sir. Yes
So
sir.
it is not a one-to-one that it is always would be the same. Yes, there are many garnets. It is also not the case that all garnets would grow or all garnets will show that the core having a lower temperature than the rim. Okay. It might also in many cases it happens that the core is at a lower temperature and the rim is at a much higher temperature. Okay, so the garnet is growing with increasing temperature. That is also possible. Okay, so we cannot fix any specific rule to any of these growth of the minerals.
Okay sir.
Okay, depends on the stability field of that mineral that and the pressure temperature path that it has followed.
Yes sir.
Okay, so now let us dig into a bit more and understand that why are we so interested in the pressure temperature time path or the pressure temperature path, for instance. Okay, so why would we spend so much time in taking all the information, taking out all the information from that of the rock and try to plot a path on the PT space? Why is it so important? Okay, that is that motivation to do this work to understand is important, and that is exclusively or most importantly because from the shape of the pressure temperature path, from the shape of the pressure temperature path, we can deduce the information, tectonic significance of the tectonic information or the tectonic setting scenario in which the rock has been metamorphosed. Okay, so we can deduce that as we can get all this information from the path that we are finding out, this finding out this path itself becomes important. So now let us see that what kind of tectonic setting would produce what kind of path and why is it so. Okay, what you see out here are three different types of path. There is path A, there is path B, and there is path C. Okay, and also we can have three types of, let's say, a model tectonic settings. We can have subduction zones, we can have magmatic accretion, and we can have contact metamorphism. Let us see that how we can relate these different paths to the different settings, so that when we get this path from a natural rock, we can directly relate to that of the tectonic setting, even if this rock presently is not, or that region from where this rock is now found does not show the tectonic setting in which it was metamorphosed. Okay, so if you think about metamorphic rock, you also think that we are not only dealing with current rocks. Current rocks means present rocks. Okay, most of the times we deal with rocks which are formed at a much older time, and we just found this. We find this on the surface. Okay, it may have been metamorphosed very, very long back. Okay, and the tectonic setting in which it was metamorphosed is completely different from where it is found now. Okay, so if we have to extract the information about that region or that area or how this rock was metamorphosed, we have to get into the details of the rock and the compositions of the rock, or the information that the rock has preserved to find all these things out. Okay, so first let us understand that in a model subduction zone, okay, that if you see a rock, that how are the pressure and the temperature changing in a subduction zone environment of a rock. Okay, and then we will try to relate that, if we can draw that change in the pressure and temperature on a PT space, and if we join that, that will give us the PT path. Okay, so here what you see is a model subduction zone. Okay, so this is a continental lithosphere on the left, there is an oceanic plate on the right. Okay, let us say oceanic a oceanic sorry, this is basically a continental lithosphere. There is a continent collision forming an orogeny or a mountain belt, right? So this is one type of, obviously, scenario where two continents are colliding, and you can see that this is the region where all the metamorphism is taking place. So this is the region where all metamorphism is taking place, and due to high pressure and the temperature, this is where majority of the metamorphism is taking place. Let us go back to a more relatively simpler situation, okay, where let us say we have a rock of the oceanic lithosphere, okay, subducting below another oceanic lithosphere or a continental lithosphere, doesn't matter. Okay, so this is the oceanic lithosphere out here. Let's say a rock, right, on the oceanic crust, or yeah, deep below, or the, let's say, oceanic crust. Okay, at the base of the oceanic crust, a rock is present. So what happens is that when it reaches the subduction zone, it moves down, right? So you'll tell me when you do not understand. As it starts moving down, okay, these are the lines. These lines are the temperature lines, the temperature at which the rock is. Let's say the rock is at roughly at 150 to 200 degrees centigrade at the base of the oceanic crust. Now it moves towards the subduction zone. It reaches the subduction zone and starts subducting, right? So what happens when it reaches the subduction zone? It moves below, okay? It moves below very rapidly, right? It moves below very rapidly. So the pressure starts increasing very rapidly because now it is much below the surface of the earth, right? There is a larger column of rock on its top, and therefore the pressure starts increasing rapidly. As you move more towards, as you move more downwards, okay, so let's say as you move more downwards out here, sorry, as you move more downwards, the pressure increases rapidly. But the temperature does not increase so rapidly as that of the pressure. Why? Because the rock is a non-conductor of heat. Okay, even it is that it is not very far from the very hot mantle. Okay, so this is the mantle, and you can see the temperatures. So thus the mantle wedge around the subduction zone is at 1000 degrees centigrade. But what you see is that the rocks do not increase the temperature so rapidly in a subduction zone, mainly because the rock is a non-conductor of heat. Okay, it takes quite a lot of time for the rock to increase the temperature, but the pressure increases instantaneously as the rock is pushed into the subduction zone. Okay, so it goes deeper and deeper to a region, okay, where let's say, yeah, so deeper to this region where the temperature increases. Okay, slowly as you move down, slowly the temperature increases. Okay, now what happens? The temperature slowly increases. Now you see the 200. So this is the 400. So you are somewhere in between. Now what happens is that many a times in the subduction zone, I don't know whether you are learning that in the structural geology or not, there are, due to tectonic processes, there are wedges or very thin parts of the oceanic crust, okay, which gets detached from this subduction zone out here on this subducting slab, and that tries to move up. Okay, that the other rocks move down, that tries to move up. Okay, so it's basically the rock is moving in the opposite direction now. Okay, so now as it moves to this region out here, so the temperature starts increasing before with slowly decreasing pressure, as now that it has slowly started moving up and the temperature starts increasing as well. Okay, temperature starts increasing as well, and then a time comes, right? Then a suitable time may come when it moves up along a tectonic peak zone very fast. It moves along the tectonic peak zone to near the surface. Okay, and this is how we actually get these rocks, the blue schist and the eclogites, in this region. Okay, so what do we see? So now if we try to plot this changing the pressure and the temperature condition of this rock, which has gone down, okay, then slowly heated up and then moved up rapidly and then moved to the surface or near surface condition and then cooled again to the temperature out here, let's say at around 200 degrees centigrade. Okay, so what do we, if we plot that on the PT path, what do we get? Okay, for that, let us now get back to this PT path. Now think about path A. Okay, so what do we see? It started, let's say around 100, 200 or whatever at low temperatures. So this is A, you consider a rock, which is of the oceanic crust, which is just started to subducting, okay, at the edge of the subduction zone. So what happens at the edge of the subduction zone, because the subduction process is relatively faster than the rock can take in heat or get heated up, so the temperature doesn't increase much, but the pressure increases very rapidly. Okay, obviously the temperature increases, but the rate of increase of pressure is very high because it is getting subducted below the surface, and it is at a much more higher depth than that of the surface. Let's around, it has reached around 30 kilometers, but the temperature is relatively much lower. So it reaches to a point where it is pressure max. Let's say for at this point, what happens? It gets detached. This rock get detached from that of the subducting slab and does not grow any further and moves its way in the opposite direction. Okay, so at this point, what happens? It reaches equilibrium about the pressure. The pressure doesn't increase much. It starts slowly going down, means it's slowly losing pressure, means going up. But as it is now in contact or more near to this hot mantle, and for a longer time, then the temperature starts increasing. Okay, so the temperature starts increasing, it reaches a particular point. Okay, and at that time, the rock starts moving upwards in a relatively faster way. Then what do we see? If it starts relatively moving faster, then the pressure starts decreasing. Okay, but as it is still near, it still takes time. Then the temperature is still slowly increasing and try to be in equilibrium with that of the surrounding mantle. So while in the decompression path, it reaches a temperature which is at the T max, and then it slowly again moves up, but the temperature also decreases, but the rate of decrease of the pressure is much higher. Okay, and we come to this point. Okay, if it is something like that, it doesn't have to be always like this A1 path. It can also be that that the temperature and the pressure decreases equally and it moves down in this fashion. So this path actually depends on that how the rock has moved up or how the rock has moved near to that of the surface. Okay, so what you see is that if you in a subduction zone, in a collisional zone, the rock which is subducted below the surface and it is moving up so that we can find it near the surface, then it always follows such a clockwise path. It doesn't necessarily mean that all the paths will have exactly the same shape, but the pattern would be very similar for any rocks in a subduction environment, the example that what I have shown. Okay, now any questions on that?
Sir,
Yeah.
in subduction zone, like we know one plate is going under like another one, so like there will be like pressure always like increasing. So after maximum, like how it's like coming back to, like I didn't get that part, like how it's lowering pressure once back.
Okay. See, the majority of the plate, one we know, so the majority of the plate is going down. Okay, it goes down into the mantle, and at some point of time, it is lost into the mantle. Okay, but only very small pieces or small layers of the rock or narrow layers of the rock, due to tectonic processes. Okay, let's say the rock is broken, right? The rock is physically broken. So what you are now doing, the thrust falls, okay, brittle fractures. I guess you are doing these in the structural geology class, right?
Yes, sir.
Okay, so there are some faults which generate in this brittle crust. Okay, so some parts are broken. Okay, and now as it is broken from this entire lithosphere which is going down, that becomes detached from the system, and due to this buoyancy of that smaller piece of rock, it starts to move up along this boundary. Okay, so there are many studies, a lot of studies, papers, and it's not so simple as I'm saying, but only if this gets physically, some parts of the rock gets physically broken, okay, that can travel up in this region. Okay, the majority of the lithosphere obviously goes down and it's completely lost. Only at near surface rocks, okay, at this contact between the mantle and the downgoing lithosphere, rocks in this region sometimes get broken, and due to physical tectonic processes, it can move up to the surface. And practically, this is how we find all the blue schist and the eclogite rocks, because they went to the depth, okay, but it did not go completely deep along with the lithosphere. It got broken in between, and moved up, and that's why we got all these rocks preserved on the surface near the subduction zone. Okay.
Yes, sir. Like it's, sir, only for like a small part, and that.
It's a much, so it's compared to this entire lithosphere, it's a very smaller part.
Okay, sir.
Okay, which can return back and come near to the surface. Okay. On
Yes.
the other hand, you can think about a continental collision zone, where also the rocks get higher when the collision happens. Then it gets the pressure increases very rapidly. Okay, if you trace the pressure temperature path of the rocks in this mountain zone, for example in the Himalayas, it will also show a similar clockwise path, maybe not exactly similar to what I have shown the example, but will also show a clockwise path where you see that the pressure increases much more rapidly. Why? Because as the collision starts, the pressure increases, the pressure is instantaneous. Okay, so the pressure on the rock is instantaneous. As the amount of rock grows on above the rock in question, the pressure will increase. But as the rock is a bad conductor of heat, it will take a much longer time to heat up. Therefore, the pressure increases more rapidly than that of the temperature. Then the temperature reaches a maximum amount, which is equivalent to the geotherm in which this rock is. And at a certain point, due to erosion, due to uplift, due to along a fault, these rocks in any of these in the mountain belt can come up to the surface, and then we will see a decrease in the pressure. Now it can also cool and decrease in pressure. Let's say there is weathering. Okay, let's say there is weathering and removal of the top of the height of the mountains. So the rocks which are present at the lower level will slowly come up. Okay, it will slowly cool and the pressure will also slowly decrease. And then we will get a path like this. Let's say it increases, the pressure temperature increases, reaches a particular time, that is the peak, and then it starts decreasing both the pressure and the temperature. We can get a path like this as well. But this is also a clockwise path. The paths may not look always the same, but a clockwise path normally indicates a more collisional zone where the pressure increases first or more rapidly than that of the temperature, followed by a decrease in pressure as well. Okay, to reach the equilibrium condition. Understood?
Yes, sir.
Sir,
Yeah.
you said we can see blue schist because of this phenomena. So,
right. See, you see this rock. Now, if you consider this example, this particular example, you see that the P max or this rock has went into the blue schist species, right?
yes.
Yeah. Now, if it preserves these conditions, then we can see the blue schist.
So is that I mean the paired metamorphic belt, is that common for
Yes.
convergent boundaries? Like
Yes,
in
that's
all
what
the
we
convergent
already
boundaries?
said. Yes. For all the convergent boundaries where there is an oceanic subduction, obviously, because blue schist, now to form blue schist, you need to have the bulk composition, which is the mafic bulk, and the oceanic crust is mafic in composition. Okay, so the metamorphism of that, this is what we got as a blue schist out here. Okay, if we consider this part would be blue schist, and we will come here that this parts we will get green schist due to the magmatic activity which is happening in this arc region, and due to the high temperature, relatively high temperature metamorphism of the continental crust, we should expect here green schist rock. Okay, so this becomes your paired metamorphic belt.
Okay, sir.
Okay, obviously.
So when the rock was coming upward, so it is not a partially melted, because in the right figure, it is some magma plumes are coming.
No, this is this I told you in the igneous, right? This is not this is the magma which is coming up. This is not the rock. The rock cannot come up through the mantle. The rocks which come up in the subduction zone is through the subduction channel, along the path where the rock is being subtracted.
Okay, so whole
It's not
rock
that
is
it
coming
gets
in.
detached from here and moves up, the rock moves up. It doesn't happen like this. It is a physical process where which there are brittle faults and faults along the subduction zone, okay, along the plate which is subducting, and it always comes up along this path.
Okay, means it is confined to a limited depth.
It is confined to a
Otherwise,
limited depth.
the rock will, yeah, otherwise it will be melted.
Yes, yes, yes. So what we get, that's why you see this path, what has moved out, the maximum temperature is around 600. So it did not go much deep. Obviously, if it goes much deep above the melting point of this rock, and from those points, it's also difficult to come up as well. Okay, so we get blue schist only in situations, for example, to get blue schist, we should have a path basically like this, okay, where it goes very strongly into the blue schist facies and come up. Now, if you have to go to the eclogite facies, then basically the rock has to go a little bit deeper to form eclogites and then come up again. So the return is from a slightly deeper area. For blue schist, the return is from a relatively shallower depth.
Yeah, okay, thank you, sir.
Okay. Okay. So now think of the path B. Okay. What do you see in path B is that the path which shows a heating to a particular temperature at a fixed pressure and cooling from that point. It's practically what we call as a heating cooling path. So what kind of rock do you think would expect such a path? If we get such a path, what kind of scenario or tectonic scenario or setting can you think of where the rock would experience such a path, that the rocks are heated to a maximum temperature and then again it cools down?
The contact meter.
Sorry?
So the contact metamorphism.
Contact metamorphism, very good. So for example, let's say you have a layer and the magma comes and gets emplaced below it. So this is the rock what we are dealing with. Okay, so the pressure doesn't increase, it's just heating from the bottom. Okay, so depending on the temperature of the magma, the temperature will rise because it gets heated to a particular temperature, and then the magma automatically starts cooling and the rock above also starts cooling, and what we get is a heating cooling path like this, which is typical of contact metamorphism. Okay, now think of the path C.
Hello, sir.
Yeah.
So why did pressure decreases in part B after?
Pressure decreases, will come to it, because with time what happens, these are all depicting natural phenomena. Okay, so with time, for any particular geologic formation, at times that there is erosion takes place. Okay, in geological time, erosion takes place. Now if you remove some part of the crust with erosion, then while cooling, then the pressure also decreases, right?
Yes, sir.
Okay, I'll show you why it's cooling as well. Okay, I'll show some diagram, draw some figures to show you that why normally it's associated with slight decrease in the pressure. Okay, maybe I can show
Yes,
you
sir.
here as well. So when there is emplacement of magma, what happens is that the crust also bulges. Let's see if I can use this eraser tool. How can erase? Okay. Okay. So what happens is that, so initially the crust was this. Oh. Okay, let's say this was the land or the crust. Okay, if you have a magma emplacement at the base, very commonly what it happens is that it slightly bulges. Okay, like this. So the pressure on this remains the same because at this point when it is heating, it's practically the same pressure. Now it has bulged a bit, and after that, along the plane line, it is eroded. So this part goes away. Therefore, the pressure on this rock now slightly decreases. So while cooling, there is a slight decrease in the pressure as well.
Yes, sir.
Okay.
Yes, sir.
Okay. So now think about part C. How can we do that? Okay. Let's say okay. We have the rock out here within the crust. Now we have emplacement of magma above and below this rock out here. Okay, so magma moving up and filling all around this place. Right? So if it is filling up all around this place, let's say, okay, then what happens? The pressure on this rock also increases. Right? Because now this is the thickness of the crust.
Yes.
Okay. So what do you see is that the temperature increases as well as the pressure increases from the initial position. Right?
Yes, sir.
Then it reaches a point which is the temperature max. And then it starts cooling because the magma starts cooling, so the temperature decreases. And this may be associated with slight decrease in the pressure. Okay, that is what we are decreasing the pressure as well. Now this can be followed by a more decrease in the pressure depending on how the crust behaves or what happens. But this is what we call as the counterclockwise path or the CCW path, which is counterclockwise, means anti-clockwise path. So any magmatic accretion, okay, what do you mean by magmatic accretion? It means that the addition of magma. Any addition of magma to the crust, okay, above and below, not really a contact metamorphism, where the crust is completely new magma is added, we normally get these anti-clockwise paths. For example, out here, this is called magmatic accretion, where magma coming in from the below and filling up different parts of the crust. Okay. Then very commonly, this part of the crust, the rocks in this part of the crust would experience, and obviously you can understand there will be magmatic mountains, and therefore the pressure increases on the crust as well. The crust becomes thicker, and therefore what we see is dominantly an anti-clockwise path, similar to that what I showed due to magmatic accretion. Okay. So now you see the beauty is that if we can find the pressure temperature path from a particular rock, from the shape of that path, we can deduce what kind of tectonic setting is it. Okay. We may not collect the rock, right, in a situation where there is an active magmatism or an active subduction. Old metamorphic rocks, we may find rocks which have been metamorphosed in a subduction zone, okay, long time, which was active long time back, but is now no longer in a subduction zone scenario. But from the information which is preserved in that rock, we can deduce what was the tectonic condition in which it was metamorphosed. That gives a very good idea, or that gives a very good information to understand the plate tectonic scenario as well. As you know that all these subduction or these are plate movement processes, and this are due to plate tectonics. Okay, so the simple information starting from the starting from the principle of geothermobarometry, from the composition of the rocks, we can get information which is on a larger scale. We can get the pressure temperature path. From that, we can relate it with the tectonic scenario, and we can get a much larger information or a much important information directly from the very rocks that you study. Okay, is that clear?
Sir,
Yes, sir.
Yeah.
sir, as you said that these rocks go in a cyclic manner, so they return back to their original state.
Yeah, they can return back to the original state. Obviously, as I said, that that part may not be recorded completely at all, then be recorded. That's why we plot or we trace only the part which can be recorded.
So my question is, if it is coming back, that means it is undergoing retrograde metamorphism. So
Yeah.
in that case, do they record the initial form that they formed? Like if it was blue schist, when it comes back, does it record blue schist?
Yes, it stays as a blue schist. It preserves that original condition in most of the cases. I think this I discussed several times, that why does it preserve? Why doesn't get back to a basalt? Okay, these obviously the blue schist materials or the minerals of the blue schist species of the blue schist rock is not stable at surfacial condition. It formed at a much higher depth and temperature than that of the surface. In fact, any metamorphic rock, okay, has formed at a pressure temperature conditions which is different from that of the surface, much higher than that of the surface. And why do we get these metamorphic rocks on the surface? Because this has stayed like that in a metastable condition.
Okay, sir.
Okay, these are not stable, but it did not change. So retrograde reactions do not go to completion always because of various reasons that I discussed, mainly the kinetic energy. So the kinetic energy barrier for the reversible reactions do not take place while retrogression with decreasing temperature. And that's why a glaucophane does not react back to the other minerals, let's say. Okay, and it preserves the condition of the peak. Okay, it gives some signatures of the retrograde metamorphism, but the entire rock does not change back in majority of the cases. And that is true for all metamorphic rocks. If it would have all returned to the condition of the surface, then we would never get a metamorphic rock which has metamorphosed to any temperature and pressure on the surface at the present day. Because any metamorphic rock has metamorphosed at a condition which is much higher than that of the surfacial condition. Okay?
Okay, sir.
Okay, any other questions? Any other questions? Okay, seems not. So now I wanted to show you, but the time may not be enough, that some conditions in which and how the path would may look like if we have certain conditions, and in what type of conditions we see isobaric cooling PT paths. Okay, you remember what you mean by isobaric cooling, and what type of settings in we can get isothermal decompression or near isothermal decompression PT paths. Okay, so the first thing, let us start and we will continue tomorrow. So the first thing what we see out here is that magmatic accretion in a thin crust, and we'll just explore the possibilities, what are the things which can happen, and then you can understand that what different kinds of PT paths we can get. Okay, and the next is magmatic accretion in a normal crust. Okay, let's think of a situation. This is what you have to work with me. Okay, Let's say we have this is the crust. Okay, you pull it. Okay, extension of this crust. So what will happen? This you have done in structural. If you pull a layer, what should happen?
It will like its length will decrease in vertical direction.
Pull it. No, the length will increase.
Increase
You
in
pull it.
horizontal direction, but height will like.
Yeah, so the height will decrease. So basically what we call as thinning. Okay.
Yes, sir.
Okay. So many a times, so most of the times what we see is that depending on where the extension is taking place, what we normally get on a larger scale, okay, some part of this crust gets thinned, right? So the thickness has decreased. Correct?
Yes, sir.
Yes, sir.
So this is the mantle below the crust, which is much hotter. Is that correct?
Yes, sir.
Yes, sir.
Okay. So think of a rock which was sitting out here. Now this rock comes here, which means closer to that of the mantle. Correct?
Yes, sir.
Okay. Let's say at a particular PT condition, this was the rock where the original rock, and this is the geothermal gradient on which it was lying. Fine? Right?
Yes, sir.
Sir.
Yeah. So now at this condition, if you extend the crust, it will move to a higher geotherm because the temperature increases.
Yes, sir.
Okay. Now you have magmatic accretion. Means there is okay. It's difficult to erase. Sorry. Oh, it's very difficult to erase out here. Just a moment, sorry. Maybe it will have to continue tomorrow. I'm not able to write. No, there's some problem. Any case, so what I was trying to say, so tomorrow we will do it in a better way. Okay, so what I was trying to say is that then the temperature increases. Okay, if we have the thin crust, and now if we have magmatic accretion, which means that there is heating of this rock. Okay, then what will happen? It will increase in the temperature. It is now in the eraser state. Okay, so it will increase in the temperature, and we have a situation like this, okay, where there is slight increase in the temperature due to the magmatic accretion, but the overall cooling of the rock will bring it back to the original geotherm. Okay, if you have the rock at a relatively higher pressure, then what happens? It heats up a bit due to the magmatic accretion, but then what you see is the cooling to the final geotherm where the rock was originally. Now, if you have a situation, the number 3, as I just showed, the magmatic accretion, how can we have this increase in the temperature as well as the pressure? If we have magma sitting on the top of the rock as well, not only heating from below, but heating from the top, which increases the pressure on the rock as well. And then it reaches a certain point, and then it cools to the original geotherm. Okay, so this is what happens. These are the different PT paths we can get when we are having magmatic accretion in a relatively thin crust. Okay, so we'll start from the one tomorrow. Okay, so thank you. If you have questions, you can ask me.